Tēnā koutou, tēnā koutou katoa. E nā manuhiri matararahi, e nā tauira, me nā kai tautoko, no mai, haere mai, ki te herenga waka. I'm Professor Margaret Hyland, Deputy Vice-Chancellor of Research here at Te Herenga Waka, and it's a pleasure to have you here this evening for this important lecture. And I think the measure of the importance of tonight's topic, as you can see on the screen, is the wide audience that we have attracted tonight. So we're honored to acknowledge the presence of honorable members of Parliament, representatives of embassies, high commissions, and the diplomatic community, members of the New Zealand Antarctic Society, the Royal Society Te Aparagi, and representatives from government agencies and ministries. A very warm welcome also to our research partners and other partners, our researchers, staff, students, and members of the wider community. Welcome to the beautiful Hunter Council Chamber. Yesterday in this room, we hosted Jonathan Lamalu, who was giving a recital and a masterclass. In a few weeks, I'm going to come along to a lecture on the setting in Shakespeare's Othello, and a little while ago, I attended a lecture here about green manufacturing of steel and what that might look like in New Zealand. And over the years, this room has hosted debates, concerts, inaugural lectures. It was once the university's library. And I mention this not just to share my nostalgia about this space, but because this room, or rather the events that take place here, represent the sharing of knowledge, expanding of understanding, and the testing of ideas which are at the heart of the university. And they were also deeply valued by Dr. Lee Sang-Ti, whose generosity has allowed us to host this annual lecture series focused on Antarctic research. The St. Lee public lecture is presented in partnership with the Victoria University Foundation, with Tupuna Patiatio, the Antarctic Research Centre, and the Lee Foundation. Dr. Lee, a distinguished Singaporean business leader, became connected with Te Herenga Waka, as these things often happen, through a personal connection with Emeritus Professor Don Trow, who he met at a reunion at the university's commerce graduates in Singapore. Renowned for his generosity, Dr. Lee was a global philanthropist who supported universities around the world. And he had a particular interest in funding libraries and lecture series because that was how knowledge could be shared quickly and widely. A valued friend of our university, Dr. Lee was awarded an honorary Doctor of Literature in 2006, and his generous support over more than 2 decades has greatly advanced our Antarctic research. And tonight we honor and we thank him for his enduring legacy. This evening, we're privileged to hear from Professor Tamsin Edwards, a renowned climate scientist from King's College London. She specializes in quantifying the uncertainties of climate model predictions, particularly for the ice sheet and glacier contributions to sea level rise. Professor Edwards provides expert advice on climate science to the public, to policymakers, media, and businesses. She was the first parliamentary thematic research lead for climate and environment, advising the UK Parliament on research evidence, and is an award-winning science communicator. And I just want to pause there because, the two parts to the work that Professor Edwards does is really important, not only that excellent science, but also the communication of that excellent science and the translation of that science into impact, into real meaning for the world. And we couldn't think of a more important question for us. And this idea of mobilization of research is something that we also at Te Herenga Waka value and encourage as much as we can. Professor Edwards' lecture is entitled Evolving Uncertainty in the Future of the Ice Sheet, and it will explore what scientists have learned since 2021 about Antarctica's stability and its potential impact on sea levels. She'll discuss how scientific understanding has evolved, what uncertainties remain, and what new insights are emerging. And I'm very much looking forward to this lecture, as I'm sure all of you are. So please join me in welcoming Professor Tamsin Edwards.
Thank you, Margaret, for that introduction. Thank you so much to the university, the Antarctic Research Centre for arranging this, for inviting me, obviously the Lee Foundation and Dr. Lee's family, the Victoria University Foundation, all of you for coming, the distinguished guests. Everyone, it's my first time to New Zealand and everyone has made me feel very, very welcome. I wish I could stay longer than the 4 weeks that I'm here. It's been flying past. So yeah, thank you very much for coming. And and I shall continue. So as Margaret said, I work on a kind of a range of things around uncertainty, ice sheets, glaciers, sea level rise. And I'm going to kind of highlight particularly the Antarctic thread of my work because of the theme of the ST Lee lecture. And I'm sure I don't need to tell any of you about the importance of sea level rise and future sea level rise as a topic, as one of the most important impacts of climate change. This statement comes from the last report of the Intergovernmental Panel on Climate Change, the IPCC, of which I'll talk more about in a moment. Sea level rise poses an existential threat for some small islands and some low-lying coasts. And this was presented in the report on the impacts of climate change on humans and other ecosystems. And I want to kind of trace back to the climate science behind that statement of existential threat. Where does that come from in terms of the scientific evidence in that IPCC report? And as Margaret said, where are we heading with the science? So we can look back at the history of the IPCC, the Intergovernmental Panel on Climate Change, who have been producing these so-called assessment reports since around 1990. So I've put a backdrop here of the growing curve of carbon dioxide levels in the atmosphere since around 1960. And that first assessment report had the acronym FAR for First Assessment Report, trying to summarize the evidence on climate change. What are the predictions? What are the impacts? What kinds of solutions might be out there? For governments, for policymakers, for the public, for people to make decisions on climate change, while the science was still much more in its early stages, although a lot was known. Of course, this was a few decades ago now. And around every 7 years or so, the IPCC puts out a new assessment report. So now in 2021 and 2022, we had the 6th assessment report. So it wasn't called SAR, that was the second, it was called AR6, usually for short. And this was produced in 3 parts. These are huge volumes, big, thick textbooks with very tiny text, a lot of words. I can't remember off the top of my head, I think it was 10,000 words, 10,000 pages across the 3 reports. And the 3 parts correspond to the 3 big aspects of climate change. The first was the climate science, the kind of work that I do, climate scientists thinking about the science of climate change. The second was that part I mentioned around the impacts on people and ecosystems. So it's called impacts, adaptation, and vulnerability. And the third was on the kind of solutions. What might we do? How effective are different ways of tackling carbon dioxide, other greenhouse gases in the atmosphere? And the IPCC doesn't make recommendations on policy on what to do about climate change. It lays out different options, assesses how they might work, different pros and cons, so that policymakers and politicians and other people can make those decisions. So kind of digging a little bit more into that first chunk of the 2021 report, that physical science basis, the climate science part of the last report. These reports take a few years to put together. This is the first author meeting in China for this report, which was in 2018. So you can see this is just the physical science part, the climate scientist part, hundreds of authors and experts there, all gathering together for that first meeting. And if we look at past the cover of this report, we can find at the very beginning this summary for policymakers, which is around 30 pages or so of the key points of the report, which are designed for the policymakers to really see what are those headline results about climate change, about how it's changed in the past, about what we know about how much humans are causing it, and what we predict for the future. So inside that summary for policymakers, flipping to one of the pages, there's lots of graphs and lots of text inside. And I'm going to talk about these two graphs, which are about sea level rise. So let's take the first one at the bottom left. This is, and apologies if you're not familiar with graphs in your day-to-day, or go through this a little bit. This is basically a prediction of sea level rise this century, or a set of predictions. And what we have kind of going along from left to right, we've got past sea level rise. This is the global average sea level rise from 1950 through to today, 2020 or so, in meters of sea level change. Relative to the past, the pre-industrial period. And then going into the future to the year 2100, we've got various different curves here in different colours and different shading. And at the bottom end here, this is a scenario of very low emissions. So perhaps keeping to the Paris Agreement targets you might be familiar with of 1.5 degrees of global warming, or trying to keep to 2 degrees at most of global warming. And here we've got about 0.5 metre or so of global mean sea level rise. And then at the sort of top end of these shaded ones here, we have the predictions under very high emissions. So burn everything, burn all the fossil fuels, keep going, kind of what in the past we might have called business as usual, but we're no longer in that business as usual. We're tackling our emissions, we're reducing that curve in the future. But this is the sort of highest emissions we might have imagined in the past that we would put out this century. Hopefully this is a scenario that we are avoiding. And that's up at about 1 metre or so of sea level rise. And these don't sound like big numbers, you're talking, you might have children that height, your knee level or hip level or whatever, these don't sound like big numbers, but actually they have very big knock-on effects on coastal flooding. So these numbers of 0.5 metre to 1 metre of sea level rise might increase the risk of a 1 in 100-year flood event by hundreds of times, 200, even 500 times on average around the world. So really, really increasing that flood risk for all the people who live on the coasts around the world. And then there's also, so I'm going to focus quite a lot on these scenarios, and then there's also this kind of dash line up at the top, this kind of dark red dash line. And this is a slightly separate thing that we that was put on the graph here. This is showing a sort of worst case scenario, almost a kind of what if or thought experiment. This is the results of a survey of experts in sea level rise and ice sheets, saying, well, what's the kind of worst possibility, the high end for Antarctica and Greenland contributing to sea level rise under very high emissions? Maybe if the computer models are underestimating, if they don't include everything, if we really put together all the worst possible, things that could happen to the ice sheets. So that was there as a sort of envelope of possibility, but the main projections are the ones at the lower end there. And so I'm going to talk a little bit today about how were these predictions made, or particularly the Antarctic part of global mean sea level, because sea level rises from Antarctic ice sheet loss, from Greenland melting, from global glaciers, and also from the oceans expanding as they warm, and from runoff from the land as well. But I'll, of course, focus on the Antarctic part today. Now let's zoom back to the other graph from that summary for policymakers. So I've now zoomed back out, and what we have here, we have the original graph at the bottom of the sea level rise this century. And then on the right-hand side, we've got predictions for sea level rise in the year 2300 on the same scale. So this is now talking meters of sea level rise. And the numbers are a bit small, sorry, but the lower blue bar is a low emission scenario again, perhaps a 2 degrees of warming scenario. And here we're seeing predictions of 0.5 metre up to 3 metres or a bit more of sea level rise. And under very high emissions, the red bar, the upper bar, we're talking 2 to 7 meters of sea level rise. So these are really coastline changing numbers, you can imagine. I mean, you know, in the UK, this would really be a huge impact, of course, the Netherlands, but everywhere around the world, these are very big numbers. But I want to talk a little bit about, because my interest is in uncertainty and thinking about how we know what we know, I want to dig a little bit into sort of how we made those predictions and where we might improve on them in the future. So these 2300 predictions were made with kind of less evidence available than the short term, this century. It's just a bit harder to predict things out to the year 2300, as you can imagine. And basically there were there's quite a limited number of studies, of predictions using computer models. And often they were using quite simplified climate scenarios where maybe actually the warming was not as high as it should be for this very high emissions. So kind of an idealized or simplified emission scenario that maybe was a little bit low. And so because there was not very many studies, there were not very many computer model studies, not a lot of evidence, the IPCC kind of supplemented this with some simple extrapolation, so kind of pretty much drawing a line from this century through to the 2300 time, and also continuing that expert survey line that I showed before, that dotted line of the kind of worst case scenario, that was extended out as well. And so this is a kind of mixed bag of different evidence. You know, it was the best we had at the time, but it meant that these predictions were kind of given low confidence because there was just not really quite enough evidence to be sure of those numbers. So I'm going to talk a little bit about how might those predictions be improved for the next assessment report. And then you might have noticed there's a dashed line extending, an arrow extending from the top of that red bar up, in fact, off the scale, which the scale here goes to about 9 or 10 meters of sea level rise. And at the top here it says sea level rise greater than 15 meters cannot be ruled out with high emissions. So that's a separate thing I'm gonna talk about as well. This is a kind of wild card prediction for Antarctica. So this is coming from a particular kind of instability of Antarctica that I'm going to talk about in a moment, which these early predictions included in this arrow here went up to very, very high numbers, very many meters more sea level rise, if Antarctica was very unstable. So this is obviously a big question mark and a big important thing to think about. So you can see just from that arrow, and perhaps you may know already, but Antarctica is the largest source of uncertainty in future sea level rise. It is the hardest thing to pin down. It has the biggest error bars, if you like, in the future, the widest range of possibilities in sea level rise. So why is that? And I forgot to add a credit, but all of the lovely photos here are from Nick Gollage here at the Antarctic Research Centre, because sadly, as a computer modeller and statistician, I haven't been to Antarctica myself. So the fieldwork photos have come from other people. Well, it's big. Antarctica has a really enormous amount of ice. I've been really interested to learn how New Zealanders often feel quite a connection to Antarctica, quite sort of aware of its presence nearby. I think much more than we in the UK feel about Greenland. So you'll be aware of quite how much ice there is, you know, tens of meters of sea level rise potential locked up in that ice, many tens. So it's big, so it has a lot of potential to add to sea level rise. It's also very dynamic. It's a moving place. This picture showing a glacier, these things are flowing ice. You know, they are dynamic things that can be unstable, can change very rapidly, and that's what we're going to be talking about a bit more in a moment. They're challenging to study, it's hard to get there, it's expensive to get there, it takes a lot of training, it can be dangerous with the weather conditions, it can be hard to get there, to get to the places you need to. And it's also a complex place. There's a lot of things going on. We've got those dynamical changes. We've got ice flow, and we've got a lot of change in the ocean, in the atmosphere. We've got snow building up the ice, as well as ice being lost into the ocean at the edges. On the dynamic point, I just want to show this, my favourite picture from NASA. This is a visualization of the speed of the ice in Antarctica. So the different colours, the deeper blue colours, are showing those glaciers, really like rivers flowing into the sea, so bringing ice from the interior of Antarctica out towards the ocean or out towards the big ice shelves, which are shown in pink there, of fast-flowing ice. And you can see kind of in the foreground, there are two sort of smaller glaciers which are ending in this kind of reddy pink colour. And this is where a lot of change has been happening in Antarctica in recent decades. We can see a picture of the mass loss, the ice loss from Antarctica from satellites, showing over about a 20-year period all this change in West Antarctica, that big dark red patch over on the left-hand side. We can see some changes up in the peninsula and that sort of spindly tail of Antarctica at the top left, and also starting in East Antarctica down on the bottom right as well. So a dynamic place, but a difficult place to study. So thinking a bit more about that dynamism, that potential for rapid change, and I think it's fair to say that a few decades ago, perhaps before some of us came into the field, Antarctica was seen as a very sort of static, inert place, very not vulnerable, just a big, huge, vast ice sheet that had been there, for as long as anyone could think of on timescales, and it would be kind of robust under climate change. But in recent decades, people have realised, particularly with satellite measurements, how much change has been going on, and therefore how much could go on in the future. So we have two types of instability that we're concerned about and that we study for Antarctica. And the first one was proposed and started to be thinking about right back in the late 1960s and the 1970s by many scientists who knew that Antarctica had been different in the past. It had been smaller, it had lost ice into the ocean, sea level rise had been higher many times in the distant past. And this idea came to be known as marine ice sheet instability. Because a lot of Antarctica is as you may know, is sitting on bedrock that is underwater. And here is a kind of sideways cut through of the ice sheet. We've got the sort of brown bedrock at the bottom, and we've got this ice sheet sitting on top of the bedrock. And then we've got ocean here, which is touching the ice. So it's kind of vulnerable to what the ocean is doing, as well as the air temperatures. And so this is the marine ice sheet because it's sat underwater, or part of it underwater. And then the idea of the instability is what you can see on this particular picture is that the bedrock is sloping downwards inland, like a sort of hill downwards. And the idea of the instability is that you can have potentially a little trigger of some melting. For example, if you have some ocean warming, if you have some warm water that touches that ice underneath, that starts a little bit of erosion and melting of the ice, and that grounding line is marked, that's the edge of the ice sheet, starts to kind of go inland from that melting. But because of the downward slope, it's a kind of unstable place to be, and it basically just keeps on going. So once you kind of nudge it, if you like, down that slope, then that grounding line, that retreat keeps going, losing ice into that ocean and contributing to sea level rise. And that's that's the sort of advancing backwards picture that you've got sideways. So that's one of the drivers of this potential instability. And then the other is this floating ice shelf that is extending over the ocean here. If that was to disintegrate, to break up, to collapse, perhaps from atmospheric warming, from the air temperature above the shelf warming and creating some melting, this kind of thing, and making that ice shelf collapse, then you lose the kind of resistance of the ice shelf. That ice shelf is acting as a bit of a brake on the glacier. So if you take that brake away, the ice can flow more easily and more quickly into the ocean, and again, start off that instability that then kind of rolls down that hill, if you like, as an analogy. So this is the idea of the marine ice sheet instability. And we have seen warmer water reaching parts of Antarctica in that region where we've seen change in West Antarctica. And we have also seen ice shelves collapsing, particularly around the peninsula that I mentioned. So this is something that we think may be underway in West Antarctica. It's a bit difficult to say for sure, but there's behaviours that are consistent with this pattern in West Antarctica. Much more recently, about 10 years ago, was proposed this new idea of instability. So this is called marine ice cliff instability. I've put in capitals here. And so here, the key thing, I've got a similar kind of picture, except you'll notice the bedrock doesn't need to be sloping downwards anymore. But here we've got a cliff, a sort of a tall cliff. The edge of the ice sheet is the sort of sheer vertical face. Perhaps you see these pictures sometimes of the ice kind of, or videos of the ice kind of crumbling into the ocean. And that could be caused, again, by an ice shelf collapsing, this floating ice shelf disintegrating, falling into the ocean, and leaving behind this tall cliff. And if the cliff is very tall, it's just unstable. It can't, be that tall. It's not. It's unstable under its own sort of weight, if you like. And so the idea of this instability is if that cliff then collapses, breaks all that ice into the ocean, the part behind it might still be a tall cliff as well, and that would crumble into the ocean, and then the one behind it as well. And almost like dominoes, the idea is that that instability would cause very, very rapid ice loss as those cliffs keep collapsing inland. And so that's that wild card of rapid sea level rise that I mentioned in the year 2300, going up to many meters more sea level rise. And I talked about those two drivers of warm ocean water or ice shelf collapse as triggering those instabilities. And unfortunately, not only are those happening in parts of Antarctica now, but they're predicted to increase in their frequency and their severity in the future under global warming. So on the left-hand side, we've got a prediction from various different computer models of how the ocean will warm all around Antarctica in the future. This is just under a sort of medium emission scenario, showing basically the fact that everything is red there shows that it's a prediction of warming oceans. So that driver is predicted to increase. And then on the right-hand side, we've got the ice shelf collapse predictions. So anything here in the kind of brighter yellow, bright green colours are where it wouldn't take very much warming from today or from pre-industrial levels to reach a critical threshold of melting over the surface of that ice shelf, and that therefore it might be vulnerable to collapse. So basically, the take home is these drivers are predicted to be more likely, the drivers of instability. So I've kind of set up, Antarctica is the largest uncertainty. There are these two instabilities we're trying to understand. I talked very little bit about computer models being the way that we start to think about the future of Antarctica. So now I want to kind of dig into those IPCC numbers and how did we get them in a bit more detail. So here is the chapter team for the last report, Oceans, Cryosphere and Sea Level Change, chapter 9. And me with the bright blue hair and Nick Gollage from the Antarctic Research Centre here met at these author meetings because we were both on that chapter team. And so again, coming back to this report, how do we come up with the predictions for Antarctica that went into those global sea level rise numbers and time series, curves into the future that I showed before? Well, as I say, computer models. So here is a simulation from a computer model of Antarctica. This is a model that my PhD students use, Nick's PhD students use, a few people around the world use. This is showing a very extreme simulation of lots and lots of ice loss over hundreds of years, just as a demonstration. But these are very sophisticated models. They have, all our understanding of the ice sheets going into them to make predictions of how the ice sheet might change, retreat, speed up, all that dynamic change under future global warming. But there's not just one computer model of Antarctica, there are many. And they each give slightly different results. They have different strengths and weaknesses. They focus on different things. And so for the IPCC reports, to try and understand the uncertainty and predictions, we have these projects which try to compare the predictions of lots of different computer models. So you'd have the one that I just showed, and then you'd have, maybe run by the group in New Zealand, and then you'd have another model run by perhaps someone in America. And so all around the world, these international comparisons are made of different predictions to try and understand the uncertainty about the future, the different possible, the different possible responses of Antarctica. And so this project is called the Ice Sheet Model Intercomparison Project, ISMIP, and it was focused on informing the IPCC. It takes a long time. This picture is our first meeting in 2014. there I am. So 7 years before the report came out. And this project was led by Sophie Nowicki in America, and the Antarctic part of it by Helene Starusi. They also looked at Greenland. And so the idea was to take all of the different computer models around the world by different universities and different Met offices and compare their predictions and average them for the future. And you can see an example here of the average predictions for different models over the century. And the blue is showing where ice is lost. You've got big ice shelves there that are showing change, but you can see more change happening in West Antarctica. But what I want to focus on is maybe not so much the exact results, but how we got there and what we did with this. So what this project did is, because it was using lots of different models, it ended up with hundreds of different simulations. So over 300 different simulations of the future of Antarctica, computer simulations. And these were made by 14 different ice sheet models around the world from these different modeling groups. And they were using different climate scenarios, high emissions, low emissions. And also, this is getting a little bit even more deeply into the science. They also looked at different ways that the ice sheet might respond. How sensitive is it to those ocean temperatures changing? Is it very sensitive or not so sensitive? What happens if you see a lot of ice shelves collapsing or not so many ice shelves collapsing? So those different possibilities were also explored in those 300 or so simulations. So that's the kind of model uncertainty, if you like. That's different choices, different possibilities that are explored with those models. And so that's great. That's a really groundbreaking project, more simulations than we'd ever had before, exploring all of these uncertainties to think about the future. But then what we wanted to do is extend that even more. So here's another graph I want to talk you through, a sort of demonstration graph. So what we're trying to understand is how much Antarctica might change under different levels of global warming. How much sea level rise would we get from Antarctica from different levels of global warming? 1.5 degrees, 2 degrees, 4 degrees, this kind of thing. And so those simulations from those ice sheet models, the computer models, they give us some data points. So you can see here what we've got is some dots in the bottom left for low global warming, giving a low sea level rise. And then going up to the top right, we've got high global warming, giving high sea level rise. Ice melts when it gets warmer, if you like. You expect that kind of relationship. And these dots are coming from those simulations. We've got a few different dots because we've got a few different models. So this is great, but you can see there's some gaps. And what if we want to know what it will do in a global warming level between the dots? And so something that I do in my research and that I'm really interested in is how to fill those gaps with machine learning. And I'm not going to go into the details of machine learning, but it's basically a kind of statistics, it's a kind of mathematics to fill those dots, to try and get a more complete picture of what's going on, to fill those gaps. So what we want to do is kind of join the dots between those simulations with these machine learning methods, just like this, just drawing a line. You could almost draw this one by hand. I've just drawn it on my slide, so that we can make a prediction anywhere along that line. So we can say, well, what if our warming in the future is 2.5 degrees of warming, but we didn't run the simulations? Our machine learning can predict what it would be, even though we didn't run the simulations. So that's the most technical bit of the talk, because that's the bit that I do. I wanted to try and give a little bit of a flavour of that. But really just the idea is that this machine learning helps us to try and predict sea level rise for any possible future global warming. And also you can do the same thing for those different possibilities I mentioned before. Any sensitivity to ocean warming, is the Antarctic ice sheet very sensitive or not so sensitive? What different scenarios of ice shelf collapse might we see? So machine learning is just adding extra information on top of those simulations. So that is how we came up with the Antarctic, most of the Antarctic predictions for those global sea level rise predictions to 2100. So those first curves that I showed of sea level rise, this was the Antarctic bit. And to give you an idea of what we found, oh, actually, before there was one more bit about the machine learning I forgot to say. Again, I'm really interested in uncertainty and making sure that the science is robust. So what you might notice about that curve is that maybe there are slightly different ways you could draw that curve. Maybe you could make it wiggle a slightly different way here. Maybe you could make it a bit more bendy down here. Maybe you could make it a bit straighter up here. And so the kind of machine learning that I do, that I think is really good, is something that tries lots of different options and lots of different possibilities, just like those different lines there. And so that's just giving you a flavour of what scientists are trying to do to understand how Antarctica will behave in the future with the computer models, and then adding machine learning on top of that to really get those fine details and understand every different possibility and every different uncertainty for the future. And so what did we find? Well, the answers for Antarctica this century were complex. So our predictions to the year 2100 were actually perhaps a bit surprising, because what we saw is that, under global warming, as you'd expect, you have more melting, you lose ice from Antarctica, you get more sea level rise from the melting. But actually, at the same time, the snowfall that falls on the ice sheet and replenishes that ice over time also increases in a warmer climate. And that might not always make sense. You associate, obviously, snowfall with winter when it's colder. But actually, over Antarctica, when it's warmer, the air can hold more moisture. We know it can hold more humidity. And so when you've got more moisture in the air, it can fall as snow. And so actually you've got more melting in a warmer climate, getting rid of ice, and you've got more snow in a warming climate, adding ice back on. So they're kind of compensating factors. You're still getting some overall loss. The melting is generally winning, but there's a bit of compensation, and it's quite hard to say how much that compensation will be over the next few decades. Different models predict different increases in melting and different increases in snowfall, how much those two things will balance out or not balance out this century. And so we found it was kind of hard to say under high emissions or low emissions scenario, the predictions were quite similar. Antarctica's going to lose some ice, it's going to contribute to sea level rise, but maybe this century it's not going to change that much with our emission scenario. At least we can't be confident in how that will change. So this is kind of like a surprising result, I think. So that's those are the results that went, one of the two results that went into those sea level curves that I mentioned at the beginning. So now so that was all the part about how we came up with the global sea level predictions to 2100 in the last report, because that related to my research. It was the bit that I worked on. But now I want to look ahead to the next report. What are we going to do for the 7th assessment report of the IPCC? So this is another picture of lots of IPCC people. This is in December, we just had the scoping meeting, which is where they invite lots of experts together to talk about what will the IPCC content be, the chapters, what are the subject of each chapters, what's the content of each chapter, because it changes a bit each time depending on what people want to know, how to organise the information. So this was the scoping meeting, and then after that they selected the experts to write the actual report. So we've got 664 experts selected from 111 countries. And we've started the process already for writing this report. So this is a preview. This is a sort of complex picture of boxes. I'm not going to go through all of it. This is the chapters of the next report, which is not, super widely known. So it's a bit of a preview, and they're not listed in order. They're listed in a big sort of grid like this. But what I just want to show is partly the chapter that I'm working on. I'm one of the leads of the global climate projections. So in the middle of this report, there's going to be global climate predictions, what's sea ice going to do, what's rainfall going to do, this kind of thing at a kind of global scale. And I kind of thought it would be interesting to point out a couple of new chapters this time that didn't exist before, which kind of reflects our current concerns as climate scientists and the concerns of policymakers who also helped steer the content of this report. So the first one is there's a tipping points chapter, so instability, surprises in the climate system. This is something that I know quite a lot of people in the public are worried about. What are the kind of the big worrying things that might happen in climate change? That's a chapter. And then there's a new chapter on basically what happens if we miss the targets of the Paris Agreement. Because obviously, you may know, we're approaching the 1.5 degrees of warming. It's becoming ever closer. So we're trying to look specifically at what will the climate change impacts be if we overshoot those temperature targets. And so we will publish a report in 2028, 2029. It's actually only just been agreed a few days ago what the timescale of all our work will be next year, but beyond that, it's not yet certain. So 2028, 29 is the current plan, and that's what we hope it will be. So a quick update on some of the new science since the last report and where that might be heading. This is a personal view. This is just my view of the work that's been done and where things are heading. We obviously want to start with this marine ice cliff instability, this kind of wild card. And in the last report, we said there was low confidence in understanding this, in simulating this. It was quite early days trying to predict this. People have looked at this now in more detail, more complete computer models, more sort of sophisticated methods. And I personally would say that the general tendency is to say that it's looking a bit less bad than we thought. So maybe it might not be so rapid, so extended and sustained. So, for example, this picture here shows if you have a cliff of ice crumbling into the ocean, it might stay as chunks at the surface of the water that sort of stick together in a mélange, as they call it. And that would act as a bit of a break and a stabilization on the cliff. So a bit like those ice shelves, the broken up ice might help to stop more cliff collapses. And there are other factors as well, but that's just one of them. But it's not certain yet, it's not agreed, it's still a bit early days. There's been a handful of studies, but I'm sure there'll be more in the next couple of years, which might help us to understand the possibility of this instability. Just coming back to those predictions for the year 2100, how have things changed there? Well, basically not that much. So there's probably more certainty about what we were starting to see. In the last report, we said there's low agreement, we have these phrases, on the relationship between emission scenario and Antarctic ice sheet response. So I mentioned about how that was a complex picture. And a study from the Antarctic Research Centre also showed the same behaviour, that actually the sort of changes in Antarctica this century don't depend very much on the emissions that we put into the atmosphere. So I'm not sure if Dan is here, but this was a paper led by him. But I don't want to say that emissions this century don't matter at all for Antarctica. They definitely do, but we see more of that change playing out later, perhaps in 100 years or more, the long-term sea level rise. So now let's look at that 2300 picture. So this was where we really had a lot of uncertainty. Remember, not so much evidence. We had some simplifications in the studies that we used. And again, this is a personal view, but it seems like the predictions are ending up a little bit at the higher end when we look at the very high emission scenario. So if we remember this red bar of total sea level rise, all sea level rise, it might be favouring perhaps the upper half or upper 3/4 of that bar for Antarctica. So that sounds bad, of course, but actually, and we're talking perhaps 3 or 4 meters of sea level rise at the top end. These pictures here show how much that would change West Antarctica. But remember I said that the previous studies were using simplified scenarios. And actually what we're seeing here is better modelling, better use of climate scenarios in the future, where people are really using a true high-end emission scenario, which actually leads to 8 degrees of global warming. So we keep on burning really everything that we can in fossil fuels up until the year 2300. We're talking 8 degrees of global warming instead of 2 or 3. And we just don't think that's going to happen. You know, we know that we're changing our emissions in the world, we're changing our technologies, we're changing our behaviours. And so we think we're heading for perhaps 2.5 to 3 degrees of warming, not 8 degrees of warming. So this is an interesting thing to look at, but this is not something we think is going to happen. This is what we avoided because we learned about climate change. And these studies explore lots of different models and uncertainty things, so, which basically means that we have much better evidence now working towards the next report. We have lots and lots more studies. They're coming up with quite similar numbers. But what we really need is more realistic scenarios. We don't want predictions just for 8 degrees of warming, because we are very sure we're not going to get to 8 degrees of warming. We need more evidence in that kind of lower end, keeping to 2 degrees or 3 degrees of warming, hopefully lower. And just the last point for that is that I want to talk about the new science is reversibility. And in the IPCC report, we said that the losses would be irreversible on decadal to millennial timescales. So on sort of any kind of human timescales, and that's obviously quite a powerful statement. And that they said that even reducing, like bringing the climate back to the pre-industrial, reversing climate change, bringing down the greenhouse gases, bringing down the temperature, if we could do that, even might not be enough to save or to bring back the ice sheet losses that we see. And so another study that comes from the group here, the Antarctic Research Centre, has said recently that there might be a bit of loss from Antarctica that we could reverse. Maybe we could save a bit of the ice sheet, but really it's reconfirming that we couldn't reverse these changes, because what we would need to do is cool the oceans right down. You really, really cool those ocean temperatures near the ice sheet. And there's more and more studies showing that that's just not possible. Even if we reduce global temperatures in the air, even if we met the Paris Agreement targets of 2 degrees, we're not bringing down those ocean temperatures enough. And so we're not going to be able to reverse any losses we see from Antarctica in any kind of, in the next few centuries. So just to kind of recap those thoughts for the next report, what I think we might be saying, or maybe I hope we can try and make clearer, that marine ice cliff instability, that scary wild card, I want to try and help us understand the difference between unlimited instability, or maybe it will be something more limited, something a bit less scary and less of a wild card. I think we're going to see this confirmation that this century the predictions are not very sensitive to our emissions, that really that's playing out over the longer term instead. At the 2300 timescale that I talked about, this is just to recap, we've got more studies, we've got more evidence, it's been done more thoroughly, so we're going to have more confidence. And maybe some of these predictions are a bit higher than the past, but that's under those very, very high emissions that we think are not going to happen in the real world. And then again, on that reversibility, I'd love to see a bit more distinction between reversing Antarctic losses in principle, if, in theory, versus what can we really do in the real world. We can't cool those ocean temperatures down. So just to give you one little advert for some upcoming work that I've been involved with lots and lots of scientists in Europe and around the world. We have a project called Protect, funded by the EU, with lots and lots of institutions around Europe, making predictions for sea level rise. And what we have been doing is trying to look at the uncertainties in Antarctica, all of those different possibilities in even more detail than before, and really get robust evidence for the future. So we've got nearly 3,000 computer simulations. Remember last time I said we had more like 300 simulations from computer models, from lots of different ice sheet models, exploring lots of different possibilities for the future, testing that the models look good. And here are those simulations going out to 2300. So lots and lots of lines here, basically, that we're going to put together into predictions for the future to try and understand this problem in more detail than ever before. And also using even more sophisticated machine learning to fill the gaps in those simulations. And so what we're trying to do in that project is come up with new predictions of sea level rise that are more complete than ever before. And I've taken the numbers off this because this was only preliminary, but this is what we want to aim for, is global mean sea level predictions to the year 2300 for all of these scenarios, not just high and low, but all of these middling ones, 3 degrees of warming, 2 degrees of warming, so that we really get the full range of possibilities for the future to inform those governments and policymakers and public around the world. So that's work in progress, hopefully out next year. But of course, there are many, many other projects, lots of work going on here, international projects around the world. You know, lots and lots of logos here, but these are all fantastic international projects looking at the past behaviour of Antarctica and the future. It's a really, really exciting time for Antarctic science. It's changing every year what we understand. So that's my update for Antarctica this year. So this is the story so far, and it may well change a bit more in the next couple of years as we get more science. We've had more modelling, better modelling to understand Antarctica. So hopefully we'll need less of that kind of expert survey and simple methods like that. We've had some questioning of that wild card of ice cliff instability. So we're going to see how that plays out in the next couple of years. Maybe those predictions are going to come down or be a bit split between the high and the low. We're hopefully seeing a bit of a difference between, you know, reversing ice sheet change in theory versus what we can do in practice. And we might see some larger uncertainties initially for predictions. When we're really exploring all those possibilities, sometimes you get a bit more uncertainty at first, but that evidence base is always getting more robust, more certain for decision makers because it's based on more information. So it's an exciting time for Antarctic research, and thanks for listening.